Hi, in this video, we want to take a look at estimating the variance term in a linear regression model, and then we're going to look at the geometric construction of our estimate for linear regression. All right, so when we think about the least squares optimization, so the formula that we worked out so far gives us an optimization formula for what the coefficients will be. It optimizes the minimum sum of squared residuals. Okay, well, something about if I look at the model, if I look at the assumptions, we assume that we have constant variance. Well, that optimization doesn't give us anything about that constant variance term. All right, so one thing that we do when we're doing multiple linear regression, we assume that the covariance between observations is 0, and we assume that the variance of the residuals is constant, now given x. All right, so something that's important about this, when I put it in this format, you see I have the identity matrix multiplied by the constant variance. Right, so on the diagonal, I have the same term every single time. On the off diagonal, I have 0. Since I have 0 on the off diagonal, the covariance between observations is 0. Now, something else that we need to realize is that the value of x, the value of our predictors, does not change the variance term at all. And this is one of the ones that when we start doing our model diagnostics and we look at the scatter plots, this is one of the ones that we check to make sure that we do not see the variance changing with our predictor variable. Right. Now, Lockheed Martin has an air show coming up this weekend, and I can hear the jets flying overhead. If this video comes out that you can't hear me, just let me know, I'll redo it. All right, so what is the variance term? Well, the variance is the expected value of y minus the expected value of y given x. So the, in a sense, this is going to be similar to our residuals, not quite, but similar. And then I'm going to be squaring it. So, and our expected value of y given x is just the coefficients times the predictor variables added up. And we'll go ahead and write this as x transpose sub I times beta, where x sub I is the ith row of our predictor matrix. So here, this is a row vector, not a column vector. Okay, well, if I think about that, I can, if this is the expected value, I can replace the expected value with this dot product. Okay, let's do that. Let's slap that in right there. Okay, so here I've got a formula for the variance term. Now let's go ahead and let's think about, well, if I have this presentation, would it be natural to go ahead and like replace this beta with beta hat to get an estimate? Yeah, that'd be reasonable. And then, I would like to do some kind of mean with it, right? We'd like to take averages, when we do estimates. So what I could do is I could replace beta with beta hat and then square the terms, add them all up for my data, and then kind of take an average. But there's going to be a catch to this. I'm not taking a regular average where I would just divide by n. I'm going to divide by n minus k minus 1. Remember, k plus 1 is the number of coefficients we're estimating. And there's a direct relationship with this. So here, this is very similar to the average of the square difference, but I'm dividing by n minus the number of coefficients. Okay, well, let's go ahead and call this s squared. Now we know that x transpose beta hat is a blue estimate of x transpose beta. Okay, so remember, blue means best linear unbiased estimator. Best means minimum variance of all the linear unbiased estimators. So if you take all of the linear unbiased estimators, this one has the minimum variance possible. Okay, so we're thinking about this, and right now we're thinking about the estimating the variance term in our assumptions. Okay, so, well, if I have this, it looks a lot like something we've seen before. Could I rewrite that? Yeah, I could rewrite this with matrix notation. So let's go ahead and rewrite s squared with matrix notation. I see that it's going to be the 2 norm of y minus x beta hat. Okay. And if we expand this out, we'll see that the middle two terms cancel out, and then we're going to end up getting this formula. All right, let's go ahead and label the numerator as the sum of squares error, because it's the sum of squares deviation between the observed y value and the modeled y value. Okay, so our next theorem is that if the expected value of y given x is x times beta, the covariance of y given x is sigma squared times I, then the expected value of s squared is sigma squared. So this tells us that the expected value of s squared is, s squared is an unbiased estimator of sigma squared. All right, well, that's good. All right, so how are we going to proceed? How are we going to do this? Well, what I'm going to do, I'm going to start with the sum of squares error. What I'm just going to go through. So here's how we define sum of squares error. So I'm going to replace the beta hat with its formula, which gives me all this junk. Remember, I've got a transpose, so everything's switched around. Now I notice I have a y transpose on the left, y transpose on the left, y on the right, y on the right. I know that I can factor the y transpose on the left, I can factor the y on the right. So let's go and do that. Now here, it's not explicitly stated, but there's an I matrix in between them. Now remember, I can always multiply by I and it will never change the result. So it's like multiplying by 1. So here, there's like an I, and we see that I right there. And then I have like the hat matrix floating around right there. Okay, so the sum of squared error is equal to y transpose on the left, y on the right, and then this particular matrix. Is that a quadratic form? Yes, it is. Oh, that's going to be great because we have formulas to deal with this. Right, we know that if we take an expected value where I have random variable, constant matrix, random variable, the same and it's the same random variable on each side, we have a special formula that involves the trace. Okay, let's go do that. So I go back, I look up that formula, I go back, several videos. I know that I'm going to take the trace of the constant matrix times the covariance of y, and then I'm going to take the expected value of y transpose on the left, the expected value of y on the right, and I put that constant matrix in the middle. All right, so now I've used the formula to figure out something about the expected value of the sum of squares error. Now, it just becomes a plug and chug formula at this point. All right, well, I'm looking at this, and I realize that the covariance of y is a constant times the identity. Okay, well, if I think about the trace formula, remember that's the sum of the diagonals. Well, if I have the sum of diagonals and I'm multiplying everything by a constant, I can factor that out because really the trace is just a special slick form of addition. Now the identity term, well, multiplying by the identity does nothing. So all I need to do is I can drop this and put this sigma squared on the outside. Okay, now this part I'm just going to leave alone for the moment. I'm going to look over here. The expected value of y is equal to beta times x, right? Or x times beta, it's x times beta. And so I replace this with beta transpose x transpose, replace this with x times beta. Boom, we've got that. Okay, so now things are coming along nicely for us. Now, in this proof, we have two identities going on. One identity is going to be an n by n matrix. The other one is going to be a k plus 1 by k plus 1 matrix. And you have to basically just know which one you're dealing with in which situation. You have to pay attention to the dimensions of your matrices when you talk about it. So right now, remember that X has n rows, k plus 1 columns. So if I want to be able to subtract X times something else, I need to have n rows in columns on this identity matrix. So this is an n by n identity. All right, so when I take the trace on this part, remember that the trace is a slick form of addition. Therefore, the trace of something minus something, I can break it up to trace minus something else. All right, so here, when I take the trace on this part, I get n, and this is just left alone. Okay, let's move over to this part, and I'm going to go through, I'm just going to distribute. When I distribute, I see that I get this times that with identity in the middle. I get this times that times that. Boom, I'm here. Okay, things are going pretty well for us now. Now, at this point, I remember the trace is commutative on the inside. So inside a trace operation, I can switch the order of matrices as long as the multiplication is defined. Okay, so I can switch the order of this business inside here as long as the multiplication makes sense. Okay. So here I change this over. So I have X times X transpose. Oh, and okay, there is a mistake in my, there's a mistake. The X transpose needs to come all the way out front. You can slap my hand when you see me. I stopped on the commutative. It needs to go out front so that I have K plus 1 for the rows out front here. Now over here, if I look, I see I have X transpose X inverse X transpose X. So I know this part here cancels out. So I'm going to get, for this part, whole thing is going to be beta transpose X beta. Well, now I notice, hey, that subtraction of that means it's going to be a big fat 0. So it cancels out. That's looking nice. Now here, if I put the transpose in the correct spot, this would make more sense. I can see that this is going to be the identity matrix. Now, realize it's a mistake here, but it will be X transpose leading. Since X transpose is leading, this is going to be an identity matrix with K plus 1 rows, K plus 1 columns. All right, when I take the trace of identity matrix, K plus 1 rows, K plus 1 columns, the trace is K plus 1. I'm doing subtraction, so this becomes N minus K minus 1. All right, so now all of this business tells us that the expected value of the sum of squares error is the variance from our assumptions times N minus K minus 1. Okay, well, how did we get here? If I was to take sum of squares error and I divide by N minus K minus 1, remember this is a constant. If I divide sum of squares error by N minus K minus 1, this equation right here tells me that the expected value will be equal to sigma squared. Therefore, the sum of squares error divided by N minus K minus 1 is an unbiased estimator of the variance in our assumption for our models. Boom, we got it. All right, so now we get something for free on this, and this is nice. An unbiased estimator of the covariance of beta hat is S squared times X transpose X inverse. Boom, we've got that. And because we know that sigma squared times X transpose X inverse is the covariance of beta hat. Okay. Now, if I look at this formula, the expected value of the sum of squares error is sigma squared times N minus K minus 1. What happens if I increase K? Well, if I increase K, then the term on the right is going to decrease, right? Okay, which means the expected value of the sum of squares error will decrease. All right, so where does K come from? K is the number of data predictor variables I have. So what this is telling me is that if I increase the number of predictor variables, then I will be decreasing the expected value of the sum of squares error. So the sum of squares error expected value decreases as the number of predictors increases. All right, so this is a justification for using more data in our linear models. Now, as we go through, we'll see that's not always a good idea, but the idea that if I have more information, I can improve my model is definitely one that seems reasonable. Okay, well, let's keep thinking about the sum of squares error stuff for a moment. I can rewrite sum of squares error in this format, which is the same as that format, right? All right, so it's a quadratic form. I've got y transpose on the left, y on the right. I have a constant matrix in the middle. Well, it's a quadratic form, therefore it's not linear. It's not linear, therefore it can't be a best linear unbiased estimator. So automatically we know it's not blue. But wait, I got something good for you. It ends up that it's going to be the best quadratic unbiased estimator of sigma squared. Okay, so if the expected value of the residuals is 0, the covariance of the residuals is sigma squared times the identity, and the expected value of each individual residual to the power of 4 is equal to 3 times sigma to the power of 4, and y is equal to x beta plus epsilon, then S squared is the best, or is a best, I should say, is a best quadratic unbiased estimator of the variance term. And the textbook references where you can look up this proof. This is a pretty well established theorem, but we're not going to go over it just because it's going to be a lot of work for the informative value. Okay, so let's think about the geometry of least squares. So what we've done so far to get the estimator of our coefficients was that we used calculus. Basically, we worked out some things that we wanted to minimize, the square deviations, and we wanted to work out certain aspects. And we've touched a little bit of expected values and variance, but we can get the line of best fit using geometry. And if I use just geometry, I don't have as many statistical assumptions as I do. Now, there will be under the hood geometric assumptions going on, specifically that we have like a straight line geometry system. That's really what's going to be the under the hood aspect of that. So if I want to look at the least squares estimate in terms of geometry, so I realize that my parameter space is a k+1 dimensional space, first and foremost. And our data space is an n-dimensional space. Okay. Now let's go ahead and say that X, the matrix X, is the one column, then our first variable, predictor variable, second predictor variable, and so on to our last predictor variable. So we have n rows, k+1 columns. Now, we're going to assume that we have at least as many data points as we have coefficients to fit. And we would prefer to have more observations and coefficients. And we're going to assume that we have full rank. So this is saying that these columns are linearly independent, like from your linear algebra course. So if we consider all possible vectors of B, X times B forms a subset of the data space, which I can write in this manner. Well, you know what? If I think about this from a linear algebra point of view, this is a subspace. And the subspace is generated by X. It's spanned by the columns of X. Therefore, X is a basis. And it's called a prediction space. X is linearly independent and spans the prediction space. So it's a basis of the prediction space. So the geometric interpretation of multiple linear regression it's really a projection. We're taking the closest point on our prediction space to the subspace that we have with our data. So we know that the expected value of y is x times beta. So our only statistical assumption in this derivation is that the expected value exists, and this is what it is. Now, I don't know what beta is, and I don't know what epsilon is. And we're going to assume that we observed x times beta plus epsilon. We observed y. The observed y is not in the prediction space. And the expected value of y given x is in the prediction space. So our approach is that we will estimate the expected value of y given x with a point in the span of x that is closest to the prediction space. Okay, now if you think about geometry, if I have a space over here and I have a point, if this is a space, if I want to take the shortest distance from this space to this point, it's going to form a right angle. There's going to be a right, so if this is my linear space, this is my point, the closest, so there's a distance from here to here. There's a distance from here to here. If I want the shortest distance possible, I have to have a right angle. And that's true in higher dimensions, whether it's 2 dimensions, 3 dimensions, or what. So what we're going to do, we're going to make the assumption that we're in like this linear space system. We've got like straight line geometry going on. And so we're going to say that, the closest point is going to have, so the closest point is going to require that y minus y hat is perpendicular to the prediction space. And so our observed residuals, y minus y hat, is going to be orthogonal to x. Okay, so from a geometry point of view, after I get my residual vector, my predictor variables have no informative value towards my residuals. This is kind of a big deal. My predictor variables have no informative value for my residuals after I perform linear regression. And geometrically, that we're saying that the vectors are orthogonal to each other, that the residual vector is orthogonal to all of our predictors. All right, well, orthogonal means that if I multiply it, I'm going to get 0. All right, well, I know that x transpose times epsilon is the same as x transpose times y minus y hat. Well, y hat is x times beta hat, right? And so now I'm going to go ahead and I'm going to distribute the x transpose. All right, so I know that x transpose times observed residuals is 0, and I know that x transpose times residuals is equal to this. Therefore, this whole thing has to equal 0. Boom, I get this. Okay, well, let's go ahead and move this over. All right, so I see that I have x transpose y is equal to x transpose x beta hat. Okay, at this point, you should be thinking, hey, this is almost a system of equations because I have, excuse me, I have a vector is equal to a matrix times unknown variables, unknown values. So I have a system of equations. Well, how am I going to solve a system of equations? Well, x transpose x is invertible by the assumptions on the rank and the number of rows compared to columns. So my solution is to multiply both sides by the inverse. All right, so I can see beta hat is exactly this. Well, that looks really familiar, right? All right, so that gives us our estimate of the coefficients. Now, if I think about this for a moment, if this is beta hat, could I go ahead and multiply both sides by x? Yeah, sure, why not? Let's do that. So if I take x, then x transpose x inverse, x transpose times y, that's equal to x times beta hat. Okay, well, let's, just for simplicity, let's go ahead and say that h is this x times x transpose x inverse x transpose. Okay, well, when we do that, I'm kind of getting ahead of myself. Now, remember that epsilon hat is y minus y hat, which is the same as y minus x times beta hat. Okay, well, so our observed residuals is our y minus x times beta hat. Let's go ahead and replace x times beta hat with this business here, which is in fact y minus h times y. Okay, well, I look here and I can factor out y on the right. Remember, so here it's implicit that I have an identity matrix. So if I factor out the y, I have I minus h subtraction times y. Okay, so now this gives me a nice formula for my observed residuals. Well, if I think about it for a moment, this is an idempotent matrix. So this is something that we touched on briefly in the homework. And I can actually represent s squared using this formula right there. And now to do this, I'm taking the residual, the dot product of the residual with itself. And then I use the fact that I minus h is idempotent. That means that I minus h squared is equal to I minus h. That's why we don't see it here. And then boom, we get our estimate. All right, that is all I've got for you. Take care and goodbye.